So how's it going, guys? Today, I want to talk to you guys about something that we all use and are probably all addicted to, online shopping. I want to talk about one aspect of online shopping that I found pretty interesting, which is the encryption portion. Now, we go to all these different types of websites like Amazon, H&M, Zara, and what we don't think about is what's actually happening with our information. You know, my parents were always talking about how they did not really trust websites to actually online shop. Like my first time when I was trying to go on Amazon to buy something, my mom took at least a couple weeks of convincing to actually explain to her why it is okay to put credit card information onto the website. So what I had to do was I had to explain to her how our information was actually being transferred from us, from our computers, to the bank and then to Amazon, and how they actually get the money. Ever since then, I really got into what encryption softwares they actually used, and I got introduced to RSA encryption. So RSA basically stands for the three surnames of three people who founded the algorithm. These people are not really that important or that relevant or needed to know for our understanding. So let me just start my explanation. RSA encryption is a method of encrypting information such as the one that's used for most credit cards. And this is important to understand for my next video, which is going to be about how we can use quantum algorithms for the future, like the algorithm created by Peter Shor, Shor's algorithm, to actually destroy this RSA encryption. RSA encryption is currently a method of encoding data so that our online shopping services is actually able to function. Without a proper method of actually encoding this data and making it trustworthy for the buyer, like myself, I wouldn't really want to do it. And it would be very, very difficult to explain to my mom why she should do it. So let's start with first understanding what RSA encryption really is. So let me explain RSA encryption in the easiest way possible. Usually this is how people explain it. Usually people say that you're basically getting two large prime numbers, you're multiplying them together to create a key, and then whatever information you're trying to send to another person, you would encode with that key. That's correct in a sense, but it gets a lot more complicated than that. So let's start off with what RSA encryption really is. Now, step one is first finding two prime numbers. These prime numbers, in our case, can be really small, like 2 and 3, or in the actual case, like in the actual world, they would be hundreds and hundreds of digits long. So these numbers can be like 200, 300 digit prime numbers. So let's say Bob is trying to send a message to me, and I'm the bank. Now, what I'm going to do is I'm going to send Bob my public key. So I'd be sending Bob two values. The value of n, which is a multiplication of our two prime numbers, which in this case would be 3 and 11, so n would be 33. So I'd be sending Bob 33 for n, and I'd also be sending Bob 5 for e. So when Bob wants to encrypt a message, he would have to encrypt it by putting his value, which let's say if he's trying to send me a 3, so he would take his 3 and put it to the exponent that I gave him, which would be 5 in this case, and then he would take mod n, which is 33. Now, this would give the value of C, which is the actual cipher message. Now, let's apply this to real life. Generally, when people are explaining this, they use the variable m for message, so we'll do the same thing. Bob wants to send a message, and the message is the number 3. Now, what he would do is he would take 3, he would put it to the exponent of e, which we have already decided, and we've sent everybody, whoever wants to send us information, and I'm the bank. And then what would happen is he would take that value, so of m exponent e, and then he would take mod n. Mod n is finding the modulus of the number, where you divide that number by n, and then whatever the remainder is, that's the value that you get, which is denoted by C. Now C is the cipher, which is the value of the encrypted message. Now Bob would be sending me C, and from C I would have to find the message that Bob wants to send me. So what I just talked about was Bob taking his value, his message, which was 3, and putting it to the exponent of 5. And this is 243. And then divides it by the number that it's telling you to take the mod by. So in this case, it's 33. So 243 mod 33, you would have to take 243 divided by 33, which is 7, take the remainder of that number, and then that's what you would get. 243 mod 33 would be 12. Now, 12 is what the C value is. C is the cipher. Cipher is the encrypted message. So Bob would be sending me, the bank, C, and then from C, I would have to find the value of M, which is Bob's message. And the reason for this is so that somebody who's trying to interfere with our message will not be able to find the value. That's why it's so complicated, and that's why it's called a one-way trapdoor function. So many years ago, when they were attempting to create the RSA encryption, they were creating a one-way trapdoor function where, without knowing some values of the actual function, you are not able to undo the function. So this is what RSA is. They're creating this function, they're creating a message, so the message sent by Bob, where the value is currently now C because of their encryption, they're sending that to the bank, which is me, and I am trying to figure out a way to decode this new message. Now, the trapdoor part is this. I am able to actually decrypt that message only because I'm the one who created the private key. Because I'm the one who created the private key, I know the two prime factors that create the letter N. The letter N, as we know from as I explained before, is the multiplication of the two prime factors that we decided on earlier, which for us is 3 and 11. So we know what the value of N is, which is 33. Now, because of the values for P and Q, which is our prime factors, that gives me the ability to create a decipher. So now, for me to actually de-encrypt the message that Bob is sending me, it gets even more complicated. Now, for me, I have to find a value of D. D is our decryption value. Now, what I'm trying to do is I'm trying to find a value of D where C, which is the cipher or the encrypted message, to the exponent of D at modulus N, which is of course the value that we got in the past for multiplying the two prime numbers, is equal to the message, which is the message in this case for Bob, which is 3. Now, finding this D value is very, very difficult without actually knowing the prime factors, because you have to go through that entire process of having N, which everybody knows because it's the public key. So everybody knows N, and you have to take N, you have to prime factor N to actually find the two prime factors, which in this case, in our very simple case, which is 3 and 11, and then you have to find the D value. Now, it's very, very difficult to find the value for D, but we don't really need to know how you can find this value. The most we need to understand is that it uses the Euclidean extended greatest common divisor algorithm to find D, which it's not too difficult for a computer to do, or even you to do, it's just very difficult to explain. But this is how you can find D, using this the Euclidean extended greatest common divisor algorithm. Now, after you find D, you have the entire loop. Now, just to sum it up, Bob wants to send a message to me. So what I'm going to do is I'm going to create a public key, which is created by multiplying two prime factors to get the value of N, which I'm going to be sending to Bob, and also a random exponent, E, that I'm also going to be sending to Bob. Now, what Bob's going to do is he's going to take his message, M, and he's going to put it to the exponent of E, and then take the modulus of N. This is going to find the value of C, which is the cipher or encrypted message. Now, what he's going to do is he's going to send the value of C over to me, and I'm going to take C, and then I'm going to put it to the exponent of D, which is my decryption exponent, which I'm going to find only because I have the trapdoor. Because this is a one-way trapdoor function, you need the two prime factors of N to find the D. And because it's very difficult to find the two prime factors of N, because of computers' limitations, I'm the only one who can find D for probably many years until Shor's algorithm, which I'll explain a little later. So now, because I have D and I have C, I can put C to the exponent of D, and then take the modulus of n, which is a public key that I already created in the past, and this will equal to the message. This is the message that Bob created right at the beginning, and it would result in me having the number 3. Now the reason I want to explain this to you is because I wanted to talk about how Shor's algorithm is going to absolutely destroy the RSA encryption method that we've been using for years. We've been using this method of encoding information for over decades. So using the abilities of quantum computers, the Shor's algorithm is actually going to be able to find these prime factors only given the n value very, very quickly, and which will give the person who's trying to interfere the message the d value also very quickly. So one of the problems that I've been explaining for normal computers is that it's very limited in finding prime factors. Now, the reason I'm saying this is because multiplying values is very, very simple for normal computers. You're taking one value, taking another value, multiplying it together. But now when you're trying to find prime factors, what our computers are currently doing is it's looking at every single value up to like half the number and just dividing it by those numbers. If a number is like, for a small number like 33, you would have to divide it by 2, 3, 4, 5. And because it's such a small number, 3 already works. And then you would be dividing 33 by 3, and then you would get 11, and then you would have the factors of Q and P. And then you would be able to find the decryption. But if it's a huge number, like a 400-digit number, you would have to go through so many different digits, just so many different numbers, just to find 2 different factors, and then you would have to find the decryption, which is very difficult. So what I'm trying to explain here is that the time complexity of multiplying numbers is actually linear compared to the time complexity of factoring numbers, which is exponential. It takes exponentially more time depending on how many numbers you have to, how many digits you have to prime factor a number. But when you're multiplying 2 numbers, it's just one process, so you can just do it at one go. But as I'm saying, that it takes division for every single digit. So you are basically testing every single number and you are dividing every single number. This is compared to only multiplying it once. So now let me try to give you a more intuitive understanding of what I mean by time complexity and how it takes exponentially more time. Let's say if there's a huge list of numbers that you have to try out to divide the n value by to find the prime factors. And imagine dividing each number takes a fixed amount of time. You would have to go through this list of never-ending numbers, and this list is constantly growing because you're constantly finding bigger and bigger numbers, and it takes a fixed amount of time for every single division operation, compared to having 2 big numbers and just multiplying them once. This is what I mean by time complexity, because the bigger the 2 numbers, the 2 prime factors are that make the huge number, that's how many times more that's how many times more time you're gonna actually take. Now in the next video, I want to really explain to you what Shor's algorithm is and the potential it has. It's going to be using quantum mechanics to actually make the process of finding these prime numbers much easier, which is going to give you the decryption key. So you're able to destroy this entire RSA encryption. Thank you for watching this video. Watch my next video if you want to understand how you can use quantum computers to destroy this current method of encryption. Thank you.